For this standard video, we're working with piecewise functions. Our objectives include reading piecewise functions, graphing piecewise functions, and then working with the absolute value function as a piecewise function. We start with reading piecewise functions and our definition. A function is a piecewise defined function. If there are specific rules which define it over different intervals of its domain. And we'll talk about that when we evaluate points here at the top and again when we actually do the graph below. But for number one, we're just going to complete the following questions for the graph here. We are just evaluating some points to start. So f of minus 6, we can see for an x value of negative 6, this function has an open circle. That open circle is an undefined point. So f of negative 6 is an undefined value. We need a closed circle somewhere to give us the function value at that point. This open circle, again, is just saying we get as close as possible to, but can never actually hit negative 6. For f of negative 5, we can see a function value there of negative 1. For f of negative 2, we've got one of our x-intercepts there on the x-axis, so a y value or function value of 0. For f of 3, we've got two options, right? One up here, one down here, but that open circle means we pick up right after 3, so we don't actually touch it. The closed circle means we do have a defined point at 3, 1, so 1 is our function value there. For f of 5, we are down on that constant piece at negative 3. For f of 6, we've got the other open and closed, our other jump, discontinuity. So we've got the open circle at the bottom, so not defined there, but as soon as we hit 6, we jump up to this other piece of the graph. So we're at 6, 2. For f of 8, we've got our other x-intercept, so function value of 0. And f of 12, we're out along that absolute value piece. There's 10, 11, 12, and we're up to, it looks like, 4. Something I didn't put on there, but just to keep refreshing it for you. If I said find values for x, so find x where f of x equals 1, again, that means our function value is 1, right, or our y value. So we're kind of looking along this line, and we can see it intersects or hits our graph 3 times. So there's 3 x values that give us a height or a function value of 1. Those x values, we saw a couple when we did the work, but we've got one at 3, one over here at 7, and a third one at 9. So there's 3 x values that give us the same y value here. Let's see, what else did we want? Domain and range, x and y intercepts. Let's do x and y intercepts. So we can still see the graph here. We can see a couple values we found when we were going through again. So our x-intercepts, we have only an x value, right? We haven't gone up or down at all. We're on that x-axis, so our y is 0. So we've got negative 2, 0, and 8, 0. We can see those are the only two places we touch the x-axis as we move along. For our y-intercept, when x is 0, so we haven't gone anywhere left or right, we just have that y movement, it looks like about a half. We could maybe find the function now because we did some stuff, but we haven't done a lot of solving yet. We'll do that later. So let's estimate now. We're just looking at the graph, about 0, 1/2. Next, we've got domain and range. I'm going to erase that red line so we can put some more stuff on here for tracking our x and y values. I think we use green for domain and red for range. So the furthest left we can go is this open circle over here at negative 6. And then as we move right, we can see there's function values for all of those. At negative 3, we have that jump, but we are, at positive 3, we have that jump, but we are defined here, so we can keep going. We're good at 6 again, and then it goes off, out, and up forever to the right with that absolute value piece. So our domain, I'll write it up here, we can copy it down there, but just so we can see the graph. We've got a parenthesis because we don't include the negative 6. We've got the open circle there, and then we're going off towards infinity. For the range, we're looking for the y values we can touch. We have values down here at negative 3. right? There's the open circles at the ends, but the infinite number of points between 3 and 6 all have a value of -3, so we touch it. And then as we're coming up the y-axis, the next place we have a point is at that -6, -2. Since it's not included, we can't include -2, but we can see the graph continues up from there, right, for any value until we get to really all the way, right? So if you think, right, all these y values can get hit. We've got our intercept there at 8, 0, starts us from the x-axis, and that piece goes up forever. So our range is going to continue off to infinity. So we can write that with a little set notation to get the -3 in. And then I'll union up with from -2 off to infinity. All right, we could put these down here just so they're in line. Maybe we got to write some more stuff up there later. So -6 to infinity for our domain. And our range, we have d value -3 unioned up with all the values right after -2 up to infinity. And we want to know discontinuities down there as well. So where does the graph have these jumps or breaks? We can see 2 jump discontinuities. Right, we're running along this piece and then we get to 3, and as soon as we get past it we jump down to this piece. When we get up to 6 we jump up to the absolute value piece. So we've got 2 jump discontinuities. We're not really worried about that endpoint, but you might see -6 listed somewhere, but I'm going to go with just the real obvious ones for you. We are discontinuous. We have a jump or break somewhere in the graph at +3 and +6 there. So both those places where we had the big jumps. So we can make sure we have jump discontinuities. All right, and then a possible equation for the function. So a couple things we want to think about. We have a square root piece all the way to the left. And so we want to think about our locator points. So we can do a couple colors. I'll do black here for piece 1. Our locator point there is -6, -2, even though it doesn't actually exist. That's that one we'd be following around. And we can see with our slope triangle, it's still up 1 over 1, just like the original square root function would be. So we just want to use that locator point in our piece here. And we'd have a y equals, with our square root, and x plus 6 underneath, right? That's minus -6, and then a -2 outside for that up-down movement. What we want to keep track of for the piecewise functions is which piece of the domain that works on. So for this one, we're going from, we'll write a little domain for that piece, -6, parenthesis again, because that open circle not included, until we get over here to 3. That 3, we'll use a bracket. And generally for these, we'll write it down below when we write the whole equation. But we're going to include set notation kind of to write those out. You'll see them more with like the x between -6 and 3 sort of thing. But we'll write it below. For 2, we've just got a constant function. Our value for there, y is always -3. And the piece we're on runs from an open 3 to an open 6, right? We don't actually include either of the endpoints for that piece of the function. And then our third piece over here is an absolute value function. So again, we want our locator point to see where our shift went. For that one, we are at 8, 0. So we shifted 8 units to the right, none up or down. You can see still the 1, 1 slope triangle like for our original function, so no stretch. So we want a y equals absolute value of x minus 8. And we can write it just like we will down there if our domain here, we've got from a closed 6 to infinity. All right, so we'll put that all together down there, and we'll write our whole equation for the graph. It's 3 pieces, so we're going to write our function f of x equals, and to use those pieces, we got this big curly brace. our first piece of the function was that square root of x plus 6 minus 2. And we can say if, right, that piece only works, -6 less than x less than or equal to 3. So the less than, right, that strict inequality correlates to the parenthesis we had before, and the greater than or less than or equal to here goes for the bracket, right, that optional equality. So the strict is a parenthesis, the optional equality has the bracket. For the middle one, we just have -3, right? It was our constant function. For that one, we were if x was between 3 and 6, right? Neither endpoint was included there because of the open circles. And for the last one, we had our absolute value function, absolute of x minus 8, if x is greater than or equal to 6, right? It started at that 6 and went off to the right forever. All right, to graph a piecewise function, kind of go in the other direction, we can still evaluate function values. We want to look for which piece of the function or which piece of the domain our x value lies in that we're trying to look at. But we can see two pieces for this function. F of x is equal to 3x minus 2. The piece of the domain that it works in is all values x less than or equal to -1. If the interval helps you see it, we can draw that. It'll also maybe help us write out the domain at the end, like the whole domain for the function. And the other piece, x squared, works for every value of x greater than -1. So from -1 off to infinity. So when we're evaluating functions, like for number 2 here, we have f of -2. We want to see which piece of that function or which piece of that domain -2 lies in. Since -2 is less than or equal to -1, we're going to evaluate by substituting it in to that first piece of the function. So our -2 gets shoved inside that linear piece, 3x minus 2. And then we can just evaluate or simplify. We get a -6, -2 when we multiply, and then a -8. So we have a point at -2, -8. For f of 2 in B, we have that 2 would be greater than -1. So we're going to evaluate that in the second piece of the function. We're going to take that 2, substitute it inside for the x and the x squared. And when we do square 2, we just get a 4. And for the last one, this is where that inequality and that strict inequality really comes into play. We're looking at -1. We do, when we graph piecewise, I'll talk about maybe 2 ways. Maybe I'll show both down there. But we really want to think about where the function or where that domain is broken. So the -1 here would be less than or equal to -1 because that's our equality. So we're going to evaluate it in the first piece of the function. But when we do the graph, sometimes it's helpful to substitute it into both pieces. And we'll look at that in a sec and how it affects the values or the points we plot. But when we multiply 3 and -1 gives us a -3 minus 2. Becomes a -5. So we'd have -1, -5 as another point on our graph. All right, to graph the function, we might not use those points. We can look back up if we need them, but there's 2 ways to do it. So 2 ways to graph. The first one is what might work for you. We can kind of see it. It'll be easy to erase on here. If you're using a pencil, you can erase with me. But the first way is to graph and erase the extra. So we'd graph like the entire function for each piece and then erase the extra pieces. And let's call that 1. The second way would be just to use the domain and graph the piece of each. And so for that graphing pieces, that's where like plugging in the -1 to both parts would work. And so maybe I'll do one and then I'll erase and I'll show the other so you can try both. I think there's room to write, or you can go on the back if you want to try both methods. But let's do the graph and erase the extra first. So we'll call it method 1 over here. Maybe I'll have room to leave both. We'll see how big I write. So we want to think first, the top part, the first function given for this piecewise function, the 3x minus 2, is just a line, right? It's a linear function. we've got a y-intercept of -2 and a slope of 3. So we can go here, m is 3, b is -2, which gives us the point 0, -2. So we can graph that line. I'm going to start at -2, and I'm going to go up 3 over 1. I've got to scale just by ones. If you want to write in some values, you can. I don't want to make it too busy, so it's kind of understood we're by 1 unless we write another scale. But we can plot some more points for that one. Get a decent line drawn up and off our graph. All right, and then what we want to look at for this piecewise part is we only wanted that piece of the line, remember, from -infinity to -1. So really now we have this point at -1, -1, 2, 3, 4, 5, -5. Trying to erase because I scribbled too many circles. But -1, -5, we've got a point. And really we want to just take that piece to the left. I don't know if I can erase just a part. I don't think I can. So pretend you're, oh, it worked. Pretend you erased with me from everything right of -1. So we just want this piece of the line, right? The whole line would be if just f of x was 3x minus 2. But since it's defined piecewise, we're only taking the piece to the left of -1. Because we've got the less than or equal to, or that bracket when we wrote out that piece of the domain, we've got a closed circle there to include the point. All right, for our second piece, I'll keep it in black. Now let's go red. For our second piece, we've got this quadratic or squaring function, right? Our toolkit function. And we know what that would look like. It's got its locator point at 0, 0. We're up 1, right 1, then up 4, right 2. And we can go up 1, left 1, up 4, left 2. We know that shape. And we could draw in that whole graph. I'm going to do a couple pieces just so maybe I can erase what I don't need. All right, and we only want the piece of that function now to the right of -1. So from -1 off to infinity, where x is greater than -1. So I'm going to erase the piece that's to the left. And because we're not including -1, we need an open circle there. So let's see, can I get rid of the extra? Not well, but we can put the open circle and then reconnect. All right, and this open circle for the red piece and the closed circle for the black piece is what ensures that we have a function still. So we can write down here, make sure your graph passes the VLT, right? We've got to make sure our graph still passes the vertical line test, or we have not graphed a function. That's not going to be good. The other method is relatively similar. I mean, we're not going to erase, but the picture will look the same. I didn't even put the red here, squaring function, right? We had that one, but we talked about our locator point. 0, 0, and then we went from there. For the second method, we generally use maybe a table of values. I can erase and redraw. You don't have to if you don't want to. You can skip ahead or watch it. If you didn't like that method, we can plot some points together. So for this one, I'd have an XY table, and I need to evaluate both pieces where the domain is split. For this one, our split occurs at x equals -1, right? We can see that break there. That's where our domain is split in half, so where our first piece ends and our second piece starts. So I like to use colors for this one. I can use some more we haven't yet. If we want to substitute into that linear function, I guess I didn't have to erase all of that, but if we're subbing into that linear function, we know for a graph 2 points define a line. So we'd have to substitute in some value in that domain. So anything left of -1, I think we did -2 above already. So we can take that point -2, -8. And then we always want to see what happens at -1. I believe we did that one up there as well, actually. So really it'd be the squaring function we're subbing extra into. So we have this point -1, -5. If we didn't already do it above, you're subbing in any value that's in that domain, left of -1 where we're split, and then also the -1. What you want to take note of is because of the inclusion of -1 there, we'd say that we're graphing with a closed circle. So we have a closed circle at -1, -5, and another closed circle at -2, -8. Really everything left of -1's closed, but might as well stress it. So -1, -5 is where that split happens, or where each piece will have an end. And for the quadratic, it's still really, really important to have that locator point. You really need to know 0, 0. And then we'd need to plug in enough points to get the shape. We always have to evaluate, like we wrote already, where the domain is split. So I have to sub -1 in here and see what happens. It's a small enough function where we maybe don't have to write out work there, right? -1 squared is just 1. But if you had a longer function, you could do your evaluation right here, just write it out and get your value for y. And then for the quadratic, generally, or the squaring function, we want to find a point left and right of that locator point. So we could plug 1 in as well. We know that's 1. It's a non-transformed toolkit function. But we can plot those 3 points, making sure that the point at -1, 1 is an open circle, because the -1 is not included there. And then we want to start there and draw our squaring function going off and up to the right. So you can see we'll get the same graph. If it helps you to just graph the whole thing, since that's kind of what we've practiced so far, graphing lines and graphing the toolkit functions with transformations, do that and then just erase the pieces you don't need. Right? Literally move left to right through the domain and just keep the part of the picture that it's on. Maybe we'll try some of that together. Or if you know the shapes well enough and how that domain affects the pieces, you can just put in a couple points to make sure you're graphing the part you need. I didn't write it in the questions, but let's do a little extra stuff since we got room and we want to keep talking about it. Our domain for this function, we had it in the pieces there. We can also read it from the graph, but one piece went from -infinity. We did green, let's do green. And -infinity up to -1, but it included it, and then the second piece picked up and kept going right. So our domain is all real numbers. And for our range, we're looking for all those y values we can hit with the function. Let's use purple because we haven't put it on the graph yet. We come from -infinity up to and including that value at -5. So we've got from -infinity up to -5 with a bracket. And then we're going to jump up to, we can see the next value we actually hit is 0 on that x-axis. And then that piece goes up forever. So we'd include 0 and go off to infinity. And might as well, one more thing, our discontinuities. Let me move it up a tiny bit so I'm not shifting the screen on us. But we can see the only discontinuity we have is at x equals -1, where we have that jump. Right, the graph is continuous everywhere else. All right, our last objective is working with the absolute value functions as piecewise functions. This is going to come up a lot more in calc when you're exploring limits. We're really just doing those. We want to get used to the notation and kind of read values from the graph. You'll do a lot more algebraically with limits in calc. But we start with a note. The absolute value function is a piecewise defined function, and then the definition of it here below. The absolute value functions, f of x equals absolute x, is the piecewise function. F of x equals part minus x if x is less than 0, and just x if x is greater than or equal to 0. And so we can see, hopefully, those are lines, right? We've got two little linear pieces together, kind of broken at the y-axis there when x is 0. The first one has that slope of -1 coming down into the origin, the 0, 0 point, and the other one has a slope of +1 going off to the right. So that's where that minus and positive comes from that we'll use as we rewrite the definitions below. For 4, we're rewriting the absolute value function as a piecewise function, and what we really want to do is isolate or identify that locator point, and we're just going to split the domain there. Right, we can see it's at that locator point or that vertex for the absolute value function where we had the split. So for this one, we can say our locator point, we can see that -2 inside would move us 2 to the right, so our locator point's at 2, 0. And there's no other transformations or anything here, so we can split it the same way the one was split above. One piece is going to be minus the original function, and we can look at exactly how that works in a sec, but we can say x less than 2, right, from that locator point, and then we have just x minus 2 for x greater than or equal to 2. So I wanted to graph just to show you here as well, and we can talk about domain and range, all that good stuff too. But we're moving 2 points to the right. There are no vertical shifts. There's no stretching or compressing or anything. So we can go with our slope triangles, up 1 over 1, up 2 over 2, up 1 left 1, and up 1 left 2 for our absolute value function. Hopefully we're just familiar with that shape now and we can kind of draw it in. But you can see that left side has a slope m of -1, right? Down 1 over 1, down 1 over 1 to get between our points. And we can even see the b there of 2. And so for our function, I can write it maybe right above. If we distribute that negative in, we get a -x plus 2. So we can see it's a linear function with slope -1 and y-intercept 2. For the other piece, we've got a slope of 1 over here, right? Up 1 over 1, up 1 over 1. And if we did kind of extend it down with that same slope, we can see it going through -2, right? That piece of it doesn't exist. We're on that negative function instead as we move that direction. So we don't actually have that intercept for this graph, but we can see how that line would continue and it matches up with that x minus 2 that we're given for the piece. Our domain, absolute value function, you can see it on the graph. It goes from -infinity to infinity, right? We can get a value for every x along the axis there, along that number line. And it'll lead us to a y value that starts at 0 and goes up. So our range would be a bracket 0 to infinity. We see, hopefully for this one, no jumps, breaks, anything in the graph, so there are no discontinuities. Even though we're defined in pieces, we'll see sometimes that those pieces link up and we won't have any jumps, breaks, gaps in the graph, right? We hit right at 2, 0 and we continue off onto the other piece. For b, we've got g of x equals 4 times the absolute value of 3 minus x plus 2. A little bit trickier. We've got some more work to do to find our locator point, but that's where we want to start. We can kind of talk about it in 2 ways there. We can manipulate the function to get it to look like the x minus h that we've done in the past. Or the other way to kind of think about this is what value for x makes this 0. And so 3 minus x, hopefully you can agree with me that if we substituted in 3 for x, 3 minus 3 would make a 0. So our locator point is going to be 3 for the x, or our h value, and then we've got that plus 2 outside, so we'll be at a 3, 2. If we do want to rewrite it, we can do a little bit of work up here. We could change the order with our commutative property, right? We can change the order for the addition, subtraction, as long as the signs stay the same. Like 3 minus 2 is the same as -2 plus 3. So this 3 minus x we can write as a minus x plus 3 inside the absolute value, and then the plus 2. And then we've got to do a little more work to get the x minus h to pop out. Namely, we want to write that negative before the other terms. So we can think factoring if you've done a little bit of it before. I know it's, I think, the next video, next standard for us, but we want to rewrite it as a negative or the opposite of x minus 3. So if I did distribute that negative back in, I'd have the minus x plus 3 I have below, and then the plus 2 there still. And so now we can see the minus 3 inside. That moves us 3 to the right, right? X minus h, so h is 3. And then we've got the up 2 from our plus 2 there. And so with that minus inside, our piecewise graph is going to change a little bit. It'll look the same because we don't really see that shift or that flip over the, it's really over the locator point. We haven't done symmetry yet, but I'll show you with the slope triangles a little bit, and we'll see why the way we write the equation will change a little bit maybe. So we'll do some work first, and we'll do some scratch. But we want to start with, let's graph the function so we can see what it looks like. I'm going to go to my locator point at 3, 2. And then I'm going to go a little higher because I know where I need to go to. We could label some points if we want. We're still just going by ones. That's 3, 4. And so if we think our slope triangles for the absolute value function, we were up 1 over 1. We could also go up 1, left 1. All right, with our stretches, compresses here, we've got that minus inside. Everything inside the toolkit function, right, we said affects the x, and everything affects it kind of the opposite of what we see. So that multiplication by -1 means we're going to divide by -1, or really it means we're going to flip kind of from left to right or right to left. So those triangles are going to go the other direction. And for the 4 outside, we're multiplying that vertical factor, the y or the vertical side of our triangles, by 4. And so we'll get some new triangles. One that goes up 4, left 1, which would have been our original up 1, right 1. So up 4 and left 1 puts us over here at 2, 6. And then this other one is flipping over, so now it's going to go to the right after we go up 4. So up 4, right 1. But 4 and 1 for both of those pieces. And the second piece now is going to the right. All right, so the graph kind of looks the same regardless of that minus, but it is going to change the way the function's defined a little bit. And we'll do some scratch work first to see it. Again, tricky function, but a good one to kind of work all the way through. So our scratch here, we'd have a 4. If we bring in the negative for that first piece, right, we have a minus a 3 minus x, just like we did on the left, and just like the original definition, we have that 1 minus piece, minus 3 minus x, and that was closed, and then plus 2. That's our whole function there. If we simplify that, we can think of it as a -4 times 3 minus x plus 2, and then if we distribute in, we get a -12 plus 4x, and then the plus 2. We can combine those like terms and write it with the x term first. So we've got our nice mx plus b equation of a line. We get a 4x plus minus 10 because the 12 is bigger there. So 4x minus 10. And if you look at this function, even though that's the piece we negated coming out, because we had a minus x to begin with, when we distribute that negative in, we get a positive x, or a positive slope here. And so you can see the right side of the graph has that slope of 4. So the first piece in that piecewise function, the one where we negate that expression inside the absolute value, isn't going to be for the pieces left of the locator point 3. It's going to be the piece to the right of the locator point here. And that's what happened with that minus inside. So we'll do a little more scratch work to write the other piece of the function nicely, and then we can get the whole function down there at the bottom. The other piece is just the 4 times 3 minus x plus 2, so we can drop that absolute value. We can distribute in, get a 12 minus 4x plus 2. Combine our like terms again, rewrite it in the mx plus b form. We get a minus 4x plus 14. And we can see again, the piece on the left side of this function has a slope of minus 4, right? Over 1 down 4 coming in, or up 4 over 1, right? That slope 4 to the right. And so when we write out our function, it was g of x here. We would have g of x equals, our two pieces would be 4x minus 10 for x greater than 3, and minus 4x plus 14 when x is less than or equal to 3. Where you have the equality doesn't matter as long as it's only on one piece, right? Our function is going to split at that vertex or that locator point, but it still connects there. So as long as that 3 is included in the function, we're good. Our domain, if we look up there quick, and our range, our domain we can see covers the entire x-axis, right? We go forever left and forever right from that locator point. So any x we sub in is going to map up to a point on our function, some y value. And while we're up here, we can talk about the range. You can see with that shift up, we're starting at 2, and then it opens up forever. So our domain would be all real numbers, or that minus infinity to infinity. Our range, we've got a bracket 2 to infinity, and no discontinuities there again. We can see the graph connects at the locator point where we're splitting that domain. There should be another I in there, but it's good. So that's it. Ask some questions if you got them. Try the ticket in the door, and we'll see you in class.